All right, welcome to 7.4 through 8.2. That's what we're covering in this lecture today. Starting in 7.4, it's the ending of chapter 7. Remember that this section will be on exam 3, not on exam 2. So in order to properly understand what we're getting into, I want you to remember where we just left off. We left off in 7.3 understanding the wave-particle duality of matter and energy, such that the smaller an object is, the more like a wave it behaves, and the larger an object is, the more like concrete matter it behaves. And an object that this directly aligns with is the electron. So that is what we're focusing on in 7.4, is how to understand the behavior of an electron. Where is it? What energy does it have? Is it close to the nucleus? Is it far away? What type of wave pattern does it take? So 7.4 examines the quantum mechanical model of the atom, which depends on the electron and the energy of an electron. More broadly, 7.4 examines the wave nature of objects on the atomic scale. An atomic orbital is not like an orbit. An orbital describes the wave function or the energy and probable location of an electron. We are able to solve for the probable location of an electron by using the Schrödinger equation. This stands for the Hamiltonian, which yields one of the allowed energy states of the electron or of the atom. This is the wave function, also known as the atomic orbital. This is the energy, and this is also the wave function, or more commonly known as psi by the symbol name. Each solution to this equation gives an energy state, an accepted energy state associated with an atomic orbital. You will not be using this equation to solve numerically for any value. We are just describing it so that you know where these solutions come from. An orbital, like I said previously, is not an orbit. It is not an exact location of where an electron resides. An electron, since it behaves like matter and like a wave, is not necessarily at one particular location at one time. But we can know the probability of its location by taking psi, or the wave function, also known as the atomic orbital, and squaring it. This gives what's called the probability density. Probability density can be seen in an electron density diagram. This is an example of the hydrogen atom and where that one electron probably lies. So if I were to describe this using a graph, with the y-axis being the probability density and the x-axis being distance from the nucleus, notice that it is more likely to find that electron closer to the nucleus than it is further away from the nucleus. You can think of a probability density map like a pitcher throwing a ball and mapping out where the pitcher is most likely to throw the ball. It's more likely that the pitcher throws closer to the catcher than further away from the catcher. Now, the probability of it throwing far from the catcher never reaches 0, but we can have a 90% certainty probability of finding the baseball in a particular space. That's the same idea as finding where an electron probably resides. So how do we describe where an electron is probably found and what type of shape this probability density map takes on? An atomic orbital is specified by 3 quantum numbers that are part of the solution to the Schrödinger equation seen above. First is the principal quantum number, the symbol n. It is a positive integer. The higher the number, the higher the energy, and the farther away from the nucleus. It gives what are called shells or energy levels. So if I say that n equals 1, I am talking about the first shell around the nucleus. The second number is the angular momentum quantum number, or the symbol L. L can equal anything 0 to n minus 1. It gives a sublevel and also gives the shape of the probability density. The third quantum number is the magnetic quantum number, or m sub L. M sub L, or the magnetic quantum number, can be anything negative L to positive L, and it gives you the particular orbital that the electron resides. Now, when we looked at angular momentum quantum number, I said that this number gives you the sublevel, or the shape of the orbital, or orbitals. What do I mean by shape? Well, each of the numbers associated with the L value, or the angular momentum quantum number, is also associated with a letter. That letter gives you a shape. When the letter for the angular momentum quantum number corresponds with S, the shape is like a sphere. As n increases, the probability density expands, and then we get P for L is equal to 1, and the shape is like a dumbbell. There is a node at the nucleus, and this is an area where the electron cannot and does not reside. The density of the electron is above and below the nucleus. When L is equal to 1, m sub L can equal negative 1, 0, and 1, so there can be 3 orbitals. When L is equal to 2, that corresponds with letter D. This is kind of like the shape of a flower. There are 2 nodal planes. That means there's 2 areas where the electron cannot exist when it's in a d orbital. When L is equal to 2, m sub L can equal negative 2, negative 1, 0, 1, and 2. So there are 5 different orbitals in L equals 2. There's also F and G, but they are not necessary to refer to here. All right, let's do some conceptualizing. You guys would be surprised with how many times I've restarted this recording. All right, let's conceptualize. What does n equals 1 even mean? What can happen in this section is that people get so overwhelmed with these different symbols that it's hard to actually tie it to something concrete. And unfortunately, there's nothing super concrete, but I'm going to try to tie it to as much of a physical understanding as I can. So what I want you to do is just visualize an atom. And as you know, an atom contains a nucleus that's positively charged, so that's right in the center here. N equals 1 is the energy level closest to the nucleus. So in order to find an electron that is in the first energy level, there's a 90% probability that it's going to be about this close. Okay, obviously this is not to scale, but this is to show you that the first energy level is most likely to be found closest to the nucleus. Okay, now what does L and m sub L and all these other different quantum numbers mean? Well, when n equals 1, L, or the angular momentum quantum number, equals 0. This is because, and if you want a reference as to why, refer to the previous slide, L can equal everything 0 to n minus 1. Yes, everything. That means all the different shapes of orbitals, or all the different sublevels that are in the first energy level is just 0. What this tells you is that there's only one type of orbital shape in the first energy level. So when L equals 0, this means that there is an S sublevel in the first energy level. There is only one sublevel because the angular momentum quantum number L can only equal 0 when n equals 1. Because as we know, n minus 1, in this case, since n equals 1, 1 minus 1 is 0. So the only available type of angular momentum quantum number is 0 when n equals 1. So this means that that energy level, that sub-level that exists in n equals 1 is an s orbital. It's a spherical shaped orbital. So what does m sub l mean? Since m sub l can be anything negative L to positive L, we have to refer back to what L equals. Okay, so these are all building on each other and they are all dependent upon what the previous quantum number equaled. So since n equals 1, this is our foundational quantum number. It's principal. It's what guides all the other quantum numbers. L can only equal 0, which means m sub L can only equal 0. Because L is 0. This means since there's only one m sub L value that is valid for n equals 1 and L equals 0, this means there is one orbital in the first energy level. This is going to make a lot more sense when we actually do electron configuration. But if you remember assigning electron configuration in a previous chemistry class, you might remember something like this: 1s2, 2s2, 2p6, blah, 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 blah. This is an example of what's called SPDF, electron configuration. And I'm just going to highlight one thing, this right here. See this little 1? This little 1 corresponds to n. That's your principal quantum number. That tells you that the electrons that I am assigning to this electron configuration, the first ones exist in the first energy level. This right here, this S, gives you your L value. So this S right here is your L. This tells you that L equals 0 because the S sublevel is what the electrons occupy. And then this right here, this just tells you the number of electrons. We're going to get more into that in the upcoming slides. But this is going to give you the foundation to understanding what all of these numbers and letters mean in electron configuration. Okay, one other thing, where do we get this idea of m sub L? Well, m sub L refers to the number of orbitals in that energy level. Each orbital can contain 2 electrons or hold 2 electrons. Okay, you don't need to write this down right now. I'm again just giving you a prelude into the rest of chapter 8. But how does this all tie in together? Again, notice right here, there are 2 electrons and they all exist in the first energy level. There is no other orbital in the first energy level. So that tells you there's only one orbital in the first energy level. That is what m sub L values give you. The number of m sub L values that you have tells you the number of orbitals that you have. So n gives you the energy level, how close to the nucleus. L gives you the number of sublevels and the type of sublevel. And m sub L gives you the number of orbitals. All right, I want you to read this question, pause the video, and then try it by yourself. And then resume to check your answers. So it asks, what are the possible m sub L values for n equals 3, and how many total electrons can exist in n equals 3? So go ahead and pause the video and then check back. All right, so here's your answer. When n equals 3, that means your L, or your angular momentum quantum number, can equal 0, 1, and 2, because L equals everything 0 to n minus 1. And they are all integers. M sub L is dependent upon your L values. So let me make this more clear. When L equals 0, M sub L is equal to 0. When L equals 1, I'm going to kind of cross over here, M sub L equals -1, 0, and 1. When when L equals 2, M sub L can equal everything -2, -1, 0, 1, and 2. Okay, so in total, that means M sub L can equal 0, -1, 0, 1, -2, -1, 0, 1, and 2, which, if I condense that down, that means my M sub L values can be -2, -1, 0, 1, and 2. But in total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. A total of 9 orbitals. Now, the m sub L value is not like the angular momentum quantum number L values. The L values give you a letter which corresponds to a shape. The m sub L values just tell you how many total orbitals there can be or exist for each corresponding shape or sublevel. I know there's a lot of verbiage here, but I have 9 total orbitals to work with. How do I find the number of electrons? Looking right here, total electrons equal number of orbitals times 2. So I can just look at this number and multiply it by 2 because each orbital can contain 2 electrons. So that's a total of 18. Or if you don't want to go through all this work of writing out all of the individual orbitals that can exist, look down here. Number of orbitals is equal to n squared. So if I take 2, which is the number of electrons in an orbital, times n squared, that gives me the number of electrons, which also gives me 18. 2 times n, which is 3, squared equals 2 times 9, which is 18. That's your final answer. All right, let's look at the next question. Go ahead and read it, and then pause, try it on your own, and then check back for the answer. It asks, what is wrong with the following set of quantum numbers? So I want to tell you something before you pause the video. The answer is not that it doesn't list all of the possible sets of quantum numbers. So these numbers correspond with one electron, with a specific electron. Each electron is assigned one of each of these types of quantum numbers. So the answer is not that, okay, well, if L equals 2, m sub L can equal -2, -1, 0, 1, and 2. That's not the answer. We're looking for a violation in the rules here because we're looking at just one electron. And for every one electron, it only can be in a certain energy level, at a certain sublevel, at a certain orbital. Okay, we're not going to list all of the different orbitals that it can reside in or all the different energy levels it can reside in. So use your rules on the previous page to kind of guide you in answering this question. All right, so the answer to this question is that L cannot equal 2. So this is what violates our rules. L can equal everything 0 to n minus 1. So it cannot equal 2. It can only equal 0 and 1. Okay, so with these numbers, we're going to use them to assign electron configuration, which really is just a method of accounting for electrons, where they reside, what energy level, how close to the nucleus, etc. All right, so you'll notice that 7.4 has a lot of information, which is why I didn't want it to be on the second exam. But more than that, it ties seamlessly into the ideas that we discussed in Chapter 8, and that's electron configuration and how to describe where electrons for a specific atom exist around the nucleus. So with those letters we just briefly went over in the previous slide, I want you to tie those to certain areas on the periodic table as seen in this image. So notice the s orbitals, or the S shape, the spherical shaped orbitals, are found on the left-hand side of the periodic table, group 1 and group 2. Whenever you're looking at an element that is in the p block, then you're looking at the elements on the right-hand side of the periodic table. Those that are in the D block are in the middle of the periodic table, and those that are in the F block are on the bottom 2 rows of the periodic table. The only time an electron is in the G orbital is when that electron is excited from its ground state. So I want you to use this as a reference for how to assign electrons and their energy levels for Chapter 8. So remember, Chapter 8 is really looking at electron configuration, or determining where electrons reside for an element, for a specific atom around the nucleus. We've already discussed 3 of the 4 types of quantum numbers. Those 3 quantum numbers are part of the solution of the Schrödinger equation, but each electron around one atom has 4 quantum numbers. The 4th one is described here. No two electrons around an atom have the same 4 quantum numbers. So you can think of it as a social security number. You can think of it as its type of identification. Those quantum numbers give not only the country that the person resides in, not just the state the person resides in, not just the city, but the specific house. Okay, so all of these 4 quantum numbers are identifying where that electron resides, and they are tied to the energy level, the sublevel, the orbital, and the spin of that electron. Let's focus on what m sub s is and what values m sub s can assume. So m sub s can be 2 different values. Can be plus 1/2 or minus 1/2. That just means that the electron is either spinning up, plus 1/2, or down. Plus 1/2 and minus 1/2 is really a convention. Plus doesn't mean it's physically spinning up. We just mean that they're spinning in opposite directions. So when an electron inhabits an orbital, the other electron that can also inhabit that orbital must be spinning in an opposite direction as the first electron. So that's why we assign one to be plus 1/2 or spin up and the other one to be minus 1/2 or spin down. Any 2 electrons in an atom can share 3 of the 4 quantum numbers, but they cannot have all 4 quantum numbers be the same. So for instance, I can have an electron that is in helium be n equals 1, L equals 0, and m sub L equals 0. One electron, though, has to have an ms value of plus 1/2, while the other electron has to have a m sub s value of minus 1/2. Okay, there are 3 guiding principles when we assign electron configuration. The first one, yes, you do have to remember the name of all of these, is called the Pauli exclusion principle. It states that there are only 2 electrons in one orbital. The Aufbau principle states that we fill electrons in the lower energy levels first before we fill electrons in higher energy levels. And Hund's rule states that electrons fill orbitals singly first with the same spin until a sublevel is full, and then they pair with opposite spins. We're going to apply this in just a little bit when we actually look at what electron configuration is, but have this handy for you to reference while we are doing electron configuration. So before we actually endeavor to use this tool on this slide for electron configuration, there are a couple things that are important to note. 2 of the quantum numbers are easily relatable to what you see on this periodic table. The first one is the principal quantum number, n. The second one is the angular momentum quantum number, L. That principal quantum number gives you the number in front of each of the letters that you see in the boxes of atoms. Second, the angular momentum quantum number, remember it gives you shape of the orbital that the electron resides in. So all of these letters, S, P, D, F, they correspond with a specific angular momentum quantum number. So when you are tasked with completing an electron configuration, keep in mind that every number and letter that you place for that configuration corresponds with an N and an L value. All right, so on to electron configuration and what it means and what you have to do. There are 2 different ways for you to express an electron configuration for any one atom. The first is SPDF notation. That should look familiar because SPDF corresponds with an angular momentum quantum number. And the second is orbital box notation. We're going to start off with our SPDF notation, and we're going to do it for the simplest atom, and that's the hydrogen atom. So this is the SPDF notation for hydrogen. Okay, why? The first thing to notice is that hydrogen has 1 electron. So the total of all the exponents, this is an exponent, for your entire electron configuration needs to add up to the number of electrons that are in that atom, that is or are in that atom. So for hydrogen, there's only one electron. Remember our three principles. The first is the Pauli exclusion principle, that there can only be 2 electrons in one orbital. The second is the Aufbau principle, and that is what comes into consideration here. The Aufbau principle states that we fill electrons in the lowest energy levels first, and then we start adding electrons in higher energy levels. So the lowest possible energy level for this one electron to reside in is the 1, first energy, S sublevel. So if you refer back to that tool that I gave you, the periodic table tool, you'll see in the upper left-hand corner that the very first sublevel that an electron can add in is the 1s sublevel. So if I'm looking at this periodic table here, notice the upper left-hand corner is hydrogen. It's in the S block, and it's in the first period. So remember, S, right here, is the sublevel, and 1 is the energy level. So 1s, and I just have 1 electron, so 1. What does the orbital box notation look like? It looks like this. The boxes are representations of orbitals, which means there can only be 2 electrons in them. The arrows represent electrons. And just a little note, remember that an arrow going up, we say has an m sub s value of plus 1/2. If there is an arrow pointing down, that means m sub s would be minus 1/2. But each orbital can only contain 2 electrons, and this does not violate that rule because there's only 1 electron in there. And then we also annotate our box and label it with the sublevel, and this is in the 1s sublevel, first energy level in the S block. Okay, let's do something a little bit more complicated. Let's look at boron. Go ahead and pause and see if you can follow this pattern to write the SPDF in orbital box notation for boron. This would be the SPDF in orbital box notation for boron. So where we start is we determine the number of electrons. Boron has 1, 2, 3, 4, 5 electrons. We start filling those electrons from the lowest energy level into the highest. So the lowest sublevel energy is 1s, and there is 1 orbital for the S block. So that means it can contain a total of 2 electrons. The second sublevel is 2s, the second period, and in the S block. And notice there's only a total of 2 boxes, which means 2 electrons, which also means there's only 1 orbital for that sublevel. Then we move on to 2p. Okay, 2p is right here. Now I want you to notice something, the number of boxes in the 2p sublevel, 1, 2, 3, 4, 5, 6. So there can be 6 electrons in the 2p sublevel total. Now for boron, it is the first electron in the 2p sublevel. That's why I have a 1 right here in the exponent. But if the p sublevel can contain 6 electrons for this row or this period, that means there's a total of 3 orbitals available for electrons to reside in. So looking at the orbital box notation, we start off again with our lowest energy sublevel, which is 1s, an arrow up and an arrow down. Remember, applying our last rule, which is Hund's rule, states that we fill energy levels first singly and then we pair them. And when we pair the 2 electrons, the Pauli exclusion principle says that they have to be opposite spins. And so one has to be spin up and the other has to be spin down. Then when we start filling electrons, we can move to the next sublevel or the next energy. And that again has 2 electrons, opposite spins. And then we go to our 2p sublevel where there's just 1 electron in the 2p sublevel. Let's mix it up a little bit and let's do it for carbon. So I'm just going to erase this. And let's see how carbon would change things. That instead of 5 electrons, we would have 6 electrons, because it just has 1 more than boron. So the SPDF notation wouldn't change too much. The only thing that would really be different is that this p sublevel would now have 2 electrons in it. Notice 1, 2. Okay, but the orbital box notation, where do we put that next arrow? Do we put it here or do we put it here? Well, you know, based off Hund's rule, that I have to singly fill all orbitals that are the same energy first. So that electron would go here. Because again, I don't want to pair electrons that are in the same energy level until all the orbitals are singly filled first. Now there's something else to notice. These are at different heights, right? That's because this is the lowest energy. And as I increase energy, my boxes get higher and higher and higher to show that the energy levels are increasing. Okay, one final thing before we move on to the next slide, and that is, what is this idea of condensed or full configurations? What we've written so far are all full configurations. We've shown all the electrons where each one resides, what sublevel, what energy level, and how many are in each of those sublevels. But there's a way to make this process expedited, especially when we get to bigger elements that have so many electrons. It takes a really long time to show where each electron resides. So let's do a condensed SPDF in orbital box notation for phosphorus. Phosphorus is right here. Okay, and it has a total of 15 electrons when it's neutral. Okay, so far we've only done neutral atoms. We haven't done charged atoms. We'll have tons of practice on that in our dry lab upcoming. Okay, so in the case of phosphorus, to expedite this process, what I'm going to do for the SPDF notation, SPDF condensed notation, is that I'm going to identify the most recent noble gas. That would be neon. I'm going to put that in brackets. So you're implying, okay, all the electrons that neon has, phosphorus also has. And in addition to that, I have these electrons. So 10 are taken care of. I have 5 more. So where do those 5 reside? That's all you need to indicate. So look at where the first electron after those 10 resides, right here. It resides in the S block and the third period. So that gives me 3s2. And then I move on to this location. I have 3 electrons that are in the 3p subshell. So that would be my condensed notation. Let's do the same for orbital box. You would still put neon, and then you would draw your boxes. 3s, 3p. I fill the 3s sublevel, and then I singly fill the 3p sublevel. The principal quantum number, which is in the first quantum number that is given or assigned to an electron, gives the period for main group elements, but doesn't necessarily give the period for transition elements. But in general, it gives you the relative distance from the nucleus. The group number at the top corresponds to the valence electrons for the main group elements only. So let's say I were to ask you how many valence electrons does nitrogen have? Okay, let's identify where nitrogen is. Right here. All I need to do is to determine what main group number it's in. This is main group. Let me take that off. This is main group number 1. This is main group number 2. This is main group 3, 4, and 5. So nitrogen has 5 valence electrons. So that's what this means. Again, the principal quantum number is just the period down here. So if I wanted to know, okay, what energy level is calcium's last electron in, you would say it's in the first, second, third, fourth energy level. And that means your N value is 4. So that's what I mean by those two statements. All right, so transition elements are a little tricky. Okay, and you'll see that they kind of have, they go around some of our patterns, change things up a bit. So transition elements have partially filled d orbitals. So those are the elements in this section, and this section. So when you are filling an electron configuration for a transition element, notice that the corresponding S, just right before D starts, that N value is bigger. So notice this is 4s, and then we go down to 3D. Okay, so that's what my second bullet point means, is that your the S subblock that's right before it fills, the electrons fill into that sublevel before they fill into 3D, which is a little counterintuitive because you would think that 3, since it comes before 4, you would fill the 3D sublevel first, but that is not the case. So if you want to use a tool like this on quiz or exam, or one of my other periodic tables that I gave you, it can be really helpful to understanding how to fill those electrons in those sublevels. Okay, third bullet point, like copper and chromium, many transition elements prefer to have half or fully filled d orbitals if possible. Okay, so let's write the orbital box notation for chromium. So have a periodic table in front of you. Try to fill out the condensed orbital box and SPDF electron configuration for chromium. And then, so pause the video, try that, and then resume once you've finished. All right, so I'm guessing most of you do not have this as your answer, but this is the answer. And this corresponds with that third bullet point. So what you might have is 4s2, 3d4. However, if the d sublevel is 1 electron away from having a half-filled or a fully filled d sublevel, that means if it can have 5 electrons or 10 electrons, if it's just one shy, it's missing just 1 electron from having 5 or having 10, that means it'll actually take an electron from the corresponding S sublevel and add it to the D sublevel. So that's why instead of having 4s2, you have 4s1. What happened is the D sublevel took that electron away. So it's easier to visualize looking at the orbital box notation. You should have 5. Notice it's half filled now, and that actually lowers the energy. That's why that happens. So an electron was taken from here and added to the 3D sublevel. So keep that pattern in mind as you're being tasked with filling out electron configurations. For intertransition elements like the lanthanides and actinides, the first F sublevel that is filled actually corresponds with a principal quantum number of 4, and the next one corresponds with the principal quantum number of 5. And so whenever you're filling periods 6 and 7, the F sublevels corresponding principal quantum number is actually 2 less than the corresponding period number. And these have some irregular filling patterns like other transition elements, so we're not going to be tested specifically on the electron configuration for lanthanides or actinides. All right, so there are 3 electron categories that you need to be familiar with. The first is inner or core electrons. I'll give you an example of each of these. Inner or core electrons are those an atom has in common with the previous noble gas in any completed transition series. So let's do an example of that. If I'm looking at chlorine and I want to know the number of inner electrons for chlorine, well, I look to its most recent noble gas. That's neon. Neon has 10. There is no transition series right before chlorine. Notice it's blank right here. So that doesn't, the transition series doesn't correspond to chlorine or anything before we get into this 3D sublevel. So again, if I want to determine the number of inner electrons for chlorine, that is going to be 10 core or 10 inner electrons because that's the number of electrons neon has, and that's its most recent noble gas. Let's do one more for one that does have a completed transition series. Let's say I asked you for the core electrons in selenium. So I would look to its most recent noble gas, which is argon, and that is 18. And I see if there's any recent completed transition series, and it does. So right before it is a transition series, and that holds 10. So selenium is 18 plus 10, and that equals 28. All right, now let's look at outer electrons. Those are the electrons that are in the highest energy level. So we look at the row or the period that is in. So let's do aluminum as an example. If I want to know the number of outer electrons for aluminum, I just look at the number of electrons that are in the third period. That is a total of 1, 2, and 3 because this is the 3s sublevel, and this is the 3p sublevel. So all of them are in the highest N value, N equals 3, 1, 2, and 3. So my answer for aluminum is 3. Let's look for, do the same thing for a transition element. Let's say cobalt. All right, so for cobalt, the rule still applies. It's those in the highest energy level. Okay, well, remember that cobalt, right here, this corresponds to 3D sublevel, and this is the 4s sublevel. So I do not count the electrons that are in the 3D sublevel as those in the highest energy level, because 3 is obviously smaller than 4. I only count the electrons that are in the 4s sublevel, and there's a total of 2. So for cobalt, the number of outer electrons is 2. All right, last category is valence electrons, and these ones are a little trickier. For main group elements, it's very, very simple. Any main group element has a number of valence electrons that's equal to its outer electrons. Also, remember the little trick from a couple slides ago, it's equal to its main group number. So any main group elements, that's electrons here or electrons here, electrons that are not in the transition series, essentially. All you have to do is look at the group number that it resides in, and that gives you the number of valence. So for example, if I wanted to know the valence electrons for carbon, I would just look at its group number. So this is group 1, this is group 2, this is group 3, and this is group 4. So carbon has 4. Could do the same thing for sulfur. Again, this is group 1, 2, 3, 4, 5, 6. So sulfur has 6 valence electrons. Really simple for main group. For transition elements, it's an additional step. So it's not only the number of outer electrons, but it's also those that are in the corresponding D sublevel. So let's look at titanium. Now, a fail-proof way to do this is first by writing the electron configuration. So let's go ahead and do that. You can write the electron configuration first before determining any of the types of electrons that you have, or the number of all the types of electrons, or you can do it the way that we've been doing on this slide. But if you want to make sure that you're doing it correct, then write the electron configuration. So for titanium, the condensed notation is argon, and then 4s2 3d2. This is the 4s sublevel, this is the 3d sublevel. Okay, so if I want to know the number of, let's say, outer electrons, it's going to be those in the highest energy level. So between 4 and 3, 4 is higher. So there's a total of 2 outer electrons. So outer is 2. But what about valence? Valence is the number of outer plus those in the D sublevel. So I have 2 here in outer and 2 in the D sublevel. So now I have a total of 4 electrons as valence electrons. So it's only tricky when you're looking at transition elements. You can use this information to help you solve for some problems that have to do with determining the number of electrons and energy levels or orbitals, etc. So if I ask for, or if you need to know the number of orbitals in a certain energy level, you just take that energy level, let's say it's 4, or 5, or 6, and you just square it. So if I'm looking for the number of electrons in N equals 3, the total of number of electrons that can be at energy level N equals 3 is 9, because 3 squared is 9. If I'm looking for the maximum number of electrons, the maximum number of electrons in an energy level is N squared times 2, because remember, there can be 2 electrons for every 1 orbital. Okay, here's we get into some craziness, some more physical chemistry, and asking, why do we have all these different sublevels? Why do we have S and P and D? Why can't everything just be in the same shape? Well, Consider the hydrogen atom. There's only one electron, so the only attraction is between the nucleus, which is positively charged, and the electron, which is negatively charged. So the energy state of that atom is just determined by the N value of that electron, which if it's at a relaxed state, N is equal to 1. Conversely, the energy state of multi-electron systems, so if you have more than one electron, that's affected by electron-electron repulsion because electrons are all negatively charged, and if they are repelling each other, then the energy changes. So what happens is energy splitting occurs in multi-electron systems. So this results in sublevels or subshells, also known as your S, your P, your D, your F. Those are different sublevels or subshells. For example, lithium. So lithium is atomic number 3, has 3 protons and 3 electrons. Why does the last electron go into the 2s subshell instead of the 2p subshell? So the question is, why does S fill before P? The answer is because 2s at sublevel is at a lower energy, but still, why is it at a lower energy? So there are 3 factors that actually dictate why energy levels split into these different sublevels. Why the second energy level splits into 2s and 2p, and why the third energy level splits into 3s and 3p and 3d. The first is nuclear attraction. So how the electrons are attracted to the nucleus. They're attracted differently to the nucleus depending on how close they are to the nucleus and if there are other electrons around. The second is electron repulsion. So if there's more than one electron, since electrons are negatively charged, they will repel each other as long as they're not in the same orbital. The third is orbital shape. So because we know that the sublevel S has a spherical shape and the sublevel P has more of a dumbbell shape, those are going to have different effects. All of these 3 factors result in the 2 phenomena known as shielding and penetration, which we get into on the following slides.